So normally computer memory is drawn as this box with lines, and each line is one memory entry. So let's say we have some memory and it has some memory places or locations or cells, call it whatever you want. We will call them memory cells for today, but it's where the data is stored. So, So each memory location has its own address so that we can select it for reading or writing. So let's say, and of course, memory addresses always start from 0. Memory addresses are written in hexadecimal format because in modern computers, for example, if you have 8 gigabytes of random access memory, it would be a very big number if we would write it in decimal, but in hexadecimal, it's actually not that long number. It's something like 9 symbols long. So this is address 0, so 0x00. Next address 0x01, next address is 0x02, and so on. So we have some amount of addresses. And this number basically tells us the size of memory. And the second variable that we have is how many bits is each memory location. Well, in practically all cases, most cases that you will ever meet with, the width of the memory is 8 bits. So 1 byte, 8 bits or 1 byte. However, this is not the only option for the following reasons. So 8 bits is 1 byte, 1 memory location. However, in program memory, as we talked about previously, for example, AVR Atmel processors, they have 16-bit program instruction length or machine code length. So, and these machine codes is the program. So there would be no use to store program, which is always 16-bit long machine codes in 8-bit memories, because then each of the instructions takes 2 bytes, and then you would have to read the first byte and then the second byte, and then do instruction. Then you read the third byte and the fourth byte, and then do the instruction. It would be slow. So for example, Atmel microcontrollers, the memory width is also 16 bits. So each memory in flash memory, in the program memory, is, for example, 16 bits. For this reason. However, for example, ARM processors, for example, ARM Cortex M3, which is a very popular architecture for some small embedded systems, its memory, well, its instructions are 32-bit. 32-bit instructions, so its memory width should be 32-bit. But in reality, it is 8 bits wide, but it jumps by 4 locations on every instruction, and it actually reads 4 bytes simultaneously. So in reality, to make it cheap, the memory is 8 bits, but it jumps by 4 locations on every instruction, and it reads, it has this superpower, this hardware acceleration, that it can read 4 bytes at the same time of program memory. And as I said previously, as a result, the size of ARM Cortex-M3's memory is given in, for example, kilobytes. Let's say, you open a datasheet and it says that the flash size is, for example, 256 kilobyte of memory. But as I said, since each instruction is 32 bits or 4 bytes, in reality, you need to divide this by 4, and you can only actually write in 64,000 instructions. You think that you have big memory in this processor, but actually the instruction count is 4 times smaller. So this sometimes causes confusion. And this is why there is a special way how to write the size of memory. And it's written in the following way. It is written as number of cells, number of cells times cell size in bits. For example, 1024 times 8-bit, which says that each memory location is 8 bits, so it's a regular 1-byte memory, and the number of such locations is 1024. We would say that its size is 1 kilobyte, but it doesn't tell you the structure. So 1 kilobyte doesn't tell you all of the information. So the important part is that it's 8 bits in each location and 1024 locations. Also, oftentimes memory is given in bits, which is even, more strange. So 1 kilobit actually looks as 8 kilo 1 kilobyte is 8 kilobits. So you go to the shop, you ask for memory, they tell you, oh, this memory size is 8 kilobits, but when you go home and calculate, then 8 kilobits actually means 1 kilobyte, and actually you get 8 times smaller memory than you initially thought. So this is why it's written in such way. And another example, for example, so as I mentioned before, for example, AVR processor machine codes are 16 bits wide. And let's say you buy a processor and its flash is too small. Many processors support memory extension where you can connect external memory to the chip, and this way you get more space. So you can actually buy a memory which is 16 bits wide. So each data location is not 8 bits, but 16 bits. Or for example, if you make a data logger and you know that all numbers that you are going to store in the flash memory are 16-bit integers, well, then you can just buy 16-bit memory instead of buying 8-bit memory and then remembering to store the bottom part of the number in one memory location and top part in the next memory location, and addressing needs to jump over 2 memory locations and so on. So you can actually buy 16-bit memory as well, and maybe even 32-bit memory. I think that probably you can buy 32-bit memory as well. It's just less popular. So for example, you go online and you can buy, for example, 256K times 16-bit. 16-bit. This means each location is not 8 bits, but 16 bits. And you have 256 times 1024 such locations. So how much kilobytes is it? It is, well, you can calculate in your head. So 256K times 2 bytes is each location. So it would be 512 kilobytes of memory. So, but if you look at it and see 512 kilobytes, you don't actually have 512 kilobytes of separately addressable bits. Actually, it's organized in different ways, so maybe your application will not work, right? So this is why you have to be careful. And its size in bits is 512 kilobits times 8. It is 4, I think it's 4 megabit. So you go to shop, you ask for some big memory, they give you 4 megabit. Then you go home, you divide this number by 8, you turn out to have just 512 kilobytes, and then you look deeper into this memory and it turns out to be 16-bit memory, so you actually can write 256,000 numbers, not 4 million numbers or something like that. So be careful with that. Oftentimes it's not really an issue, but you can just make these mistakes. So let's go online. I don't know, where do we want to go? We want to go to, for example, farnell.com. It's a very popular shop. So it's in Latvian language. I don't know, can I change it to English? Okay, so we go to semiconductors. For example, we want to buy this memory. Then we go to blah, 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 memory. Here we enter the memory part. In this shop, you can go online, register, buy with your credit card, and it will ship the chips next day delivery they have. And, it's shipping some like €5 or something. So for example, we want, I don't know, we want flash memory, whatever. And here we can select all kinds of memory. We can also order them by price if we want to. Let's see, in stock, show results. It says show results. And, you can buy some like memory for 30 cents, right? So it's cheap. But now we can also select the size of memory, but the size is given in these bits. So if you need, for example, 1 megabyte of memory, then you actually need to buy 8 megabits of memory. 8 divided by 8 is 1, then you get 1 megabyte of memory. These cheaters. The largest that you can find in this, for example, shop is 128 gigabit. If you divide it by 8, how many gigabytes is it? I don't know. It's something like 2 gigabytes or something. 128 divided by 8 is 16 gigabytes of memory you can buy. And here is flash memory configuration. As you can see, it says sometimes, this pages and bytes is wrong. This is not, this is a bad way to write it, so we will ignore it. And here it says, for example, 1024K, which means 1 mega times 8-bit. And here you can see there's also a memory, 128 words, but each location is actually 16 bits. These are specialty memories. They're not very popular, but you can buy such memory. But as you can see, most of them are actually 8-bit memories, and some rare cases are 8-bit. And you can see here, for example, some memory can probably switch between 8-bit mode and 16-bit mode. But I don't see 32-bit memories here. Probably they don't exist. Okay. But random access memory should be 32-bit because many ARM processors support random access memory extension. So DRAM, ferroelectric, FIFO, flash, static RAM. Well, I hope that static RAM is 32 bits wide. Blah, blah, blah. Here it is 36 bits. Oftentimes, the memory is not 32 bits, but 36 because 4 bits are used for error detection and correction. So instead of sending just 32 bits from chip to processor, it sends 4 extra bits for error detection. And for example, if it sees that the parity bits are wrong, well, then it knows that some error happened during transmission and they send the bit once more. It just pauses the processor and tries to read the memory again. So pretty smart technologies. Okay, so here it is, 512K times 36 bits, because it has error correction and detection. Okay, so that is about the way the memory is organized. And well, when we're talking about microcontrollers, practically always the memory is just 8 bits and you don't have to worry about anything. It's just 8-bit memory. Okay, that was about terminology. Now I will delete this, just memorize it. Now we will talk about 8-bit memory. So, how can we use this 8-bit memory? The fundamental cell of memory, I think we already talked about it last time, is this cell, which is really similar to our general purpose register memory cells. Let's say basically all memory locations have some data input through which you can write a new value into the memory cell. It also has data output through which you can read the value that is stored inside the memory location. Then, to control reading and writing, you would also have some kind of clock signal so that writing happens at certain uh, moment in time. You know, for example, you first set the input, then you wait for the signals to come from CPU to this memory cell. You wait for a moment, I don't know, some microseconds, and only then you give clock signal, which is rising edge, which forces the data to be written in this location and outputted to Q. So, you know, so that it doesn't happen at random times, it happens when the clock makes a rising edge. So some clock signal. And then, since we have many locations, we also need to control which memory location is updated and which memory locations are not touched. For example, if you want to select only certain memory location for update, we also need some kind of control signal, which we will call write enable. Write enable. So if write enable is low, you can clock all day, you can input data all day, it's not going to be written into the memory cell. But if you set write enable high and set the data to the new value, and then you give clock rising edge from 0 to 1 during transmission moment, it will store whatever is shown on data lines. So that would be like each memory cell is built like that. So I can write, for example, 8-bit. You know, it's just 8 bits is 1 bit times 8 copied 8 times. So how do we read from this memory? So this memory is huge. It has, for example, 1000 entries, 1000 bytes. How can we read from it? Well, we need to use a big multiplexer and a select signal, just like we did on this general purpose register case. So each memory cell output Q is connected to this multiplexer, and there will be a select signal which decides which of these inputs will be forwarded to this single output, which is the output of the whole memory chip. So, oops. So there is this select signal, and we will call it read select cell. And here is the output. This is like the queue, which is the big queue, which outputs one of the selected cells. So with, for example, I don't know, let's say memory location 0 has a value 77. Memory location 1 holds value, for example, written previously 42, the answer to all questions of universe. Next location, for example, holds 69. Next holds, for example, 255, whatever. Now, let's say we want to read the contents of memory location number 01. So with this read select signal, we set it equal to 0x01, which is basically 0001, whatever the number of bits. And this selector just forwards the output of memory cell number 1 to this general output, this data out. So this data out shows number 42. You know, this multiplexer just selects input number 1, which gives the number 42. So this way we can read from memory. With this read select, we select the address and its contents are output to queue. You know, for easier understanding, I can write, for example, the name of this pin will be data out. Okay. This is reading. Reading is easy. Next question is, how can we write something into this memory? So we will use this write enable signal to switch on writing mode only to one of these memory cells. And just like in the case of general purpose registers, which we did in our lab, or not yet, you didn't have this lab yet, but you will have it this week, I think. So we have an element which is called selector, and it's similar to multiplexer, but well, actually, it's like demultiplexer. Actually, yeah, that's what it is. So demultiplexer. So we have this input write enable. I'll just write it here. And we have a control signal, which we will call write select. And with this, we will just forward this write enable to one of these many cells. So for example, if I set write select equal to 3, then write enable will be forwarded to cell 3. All other cells will be equal to 0. So all other cell write enable signals will be equal to 0. So they will be disabled for writing, and only this one cell, for example, cell number 3, will be active, and it will receive this write enable signal. So, you know, all cells have this write enable connected, but only one of them receives this write enable signal. Other cells have this write enable signal equal to 0. So it's not active, and the data that's put on input will be just ignored. Like this. So for example, if I set write select signal equal to 3, 0x03, for example, then this write enable signal is forwarded to cell number 3, and this cell will be overwritten on rising edge of the clock. So let's just connect also the clock signal. So the clock signal is basically just directly connected to all cells because we control writing with this write enable. So this clock enable, or simply clock signal, basically it just connects to all cells. It's connected to all cells. And we also have this data in. So I'll call it D, data signal. D, and with light gray, I will write data in. Like this. So, and data in can also be connected to all cells. You know, each data bit is connected to each bit of each cell. How can we do that? For example, if we have this memory chip, it has many layers, and one of the layers is just data lines going over all memory cells and then just connecting to each cells each bit. So for example, data in 8 bits, and each bit connects to the certain bit of each cell. And you know, data goes to all cells, but it will be stored only in that one cell, which is selected by write enable and write select. Other cells, yes, they receive this data at input, but they just ignore it because write enable for other cells is off. Okay, so for example, we select write select equals 0x03, so cell number 3 is selected. Write enable, we set high equal to 1. Data we set, for example, I don't know, 120. And when we do the clock from low to high, then this 255 is overwritten by 120. Okay. And then we set clock low, and then we set write enable equal to 0. And on the next rising edge of clock, nothing will be written anywhere because write enable is 0. Okay. So this is how writing works. Okay, so on one side we have read. We read information by selecting the cell and outputting it to data out. And we write by putting data in, write enable, select the memory location which to write, and then we do clock rising edge, and it stores the value. And then on falling edge, we, for example, switch off all the signals. Okay. Now, you know, this is how we could build the memory, is no problem, but there is one small problem, which I will now ask you to answer in the chat. Please be prepared to answer some very, very simple question. Question number 1. So, if this is 8-bit memory, how many wires go from this data out? How many cables go to the CPU? So if this is 8 bits, how many wires go from data out from Q to the processor? Write it in the chat. Don't be afraid to make mistakes. So somebody says 2. Okay, maybe, but the problem would be we, for example, want to output a number 120, or we want to output number 255, so it's 8 bits. So we need 8 data lines because each of them will show 1 bit. So maybe with this one I'll help, and the next one you will have to calculate yourselves. So the number of cables going out, data out, it is 8 wires. Because it's 8 data bits and each wire shows one of these bits. They will be, of course, ordered 7 to 0. You know, they will be numbered, they will be in certain order. But basically, Q is 8 wires. And if we look at computer memory, I think the newest version of computers has 64-bit memory, if I'm correct, because these are 64-bit processors. So, you know, program memory should also support 64 bits. So at you know, more advanced computers, instead of 8 bits, it would be 64 wires, which is a bunch of wires. It's a big number of wires. But 8 is also, you know, not a small number. Next question, how many wires is data in? If we can input 8-bit numbers, then the number of wires at data in is 8. Well, they are also numbered 7 to 0. Okay, some numbering. Next question, how many wires is clock signal? 1 wire, because you just clock, it goes from high to low or low to high, but it's basically 1 wire. You know, it's just 1 signal. How many wires is write enable? Write enable is 1 wire. And now I will tell you this extra information and then the next question. Let's say that our memory is 32 kilo times 8 bits. So, well, it's just 32 kilobytes of memory. How many bits is read select signal and how many bits is write select signal if we need to be able to select each one individually, each one of these 32,736 memory cells. How many bits is read select and how many bits is write select? So 256 bits. Maybe, how did you calculate it? Maybe some other answers, some other options. Well, it's actually less, but let's think about it. So if we have to switch between 2 inputs, we basically need just 1 bit. If it's low, it's input number 0. If it's high, it's input number 1. So to switch between 2, we need only 1 bit. Either it's low or it's high. If we need to switch between 4, we need 2 bits. 0, 0 will be first input, 0, 1 will be the second, 1, 0 is the third, and 1, 1 is the fourth. If we need to switch between 8 inputs, we need 3 bits because it's 2 to the power of 3 is 8 combinations, right? If we need to switch between 16 inputs, we only need 4 bits because 2 to the power of 4 is 16. So with 4 bits, we have 16 different combinations. And now you can just, you know, repeat it until you reach 32,736 different combinations. How many bits do we need to select between 32,000 combinations? So 1k is 1024 equals to 2 to the power of 10. So to switch between 1000 different combinations, we only need 10 bits because 2 to the power of 10. 2 to the power of 10 is 1024, and 32, whoops, that's an ugly 30. 32 is 2 to the power of 5. So we need 5 bits to switch between 32. So if we multiply them, you probably know from middle school algebra that these exponents add. So 32k is 2 to the power of 15. So we need 15 bits. So read select is 15 cables or 15 bits, and write select is also 15 wires or 15 bits, the same. So I'll just delete it here. And I'll just write it here. So read select is to switch in this case, of course, if the memory is bigger, you need more bits. But in this case, it's 15 wires, and they are, of course, numbered from 14 to 0. And write select is the same, 15, because we can select for writing also the same number of cells. So it's 15 wires, numbered from 14 to 0. Okay? So if we double the memory, we need to add one more bit. So for example, 64K will be 16 wires. 128K will be 17 wires, and so on. And by this logic, you can solve this mystery why some Windows versions and older computers and older Windows versions only support 4 gigabytes of RAM and no more. Well, it's quite simple. How much is 4 gigabyte? 4 gigabyte is 4 times 1024 times 1024. This will give kilobytes, this will give megabytes times, and this will give gigabytes, which is 2 to the power of 2 times 2 to the power of 10 times 2 to the power of 10 times 2 to the power of 10 equals 2 to the power of 32. So it's just that the motherboard has only 32 wires going from CPU to random access memory. So the motherboard physically can only select between 2 to the power of 32 different memory locations. And also in older Windows versions, the pointer size was 32 bits. As a result, the pointer also could point only to one of 2 to the power of 32 different locations, and it's just 4 gigabytes, right? So, question to you, is it a good solution that we simply increase the number of wires and the pointer size? Let's say that the pointer will now be 2 to the power of, to have 8 gigabytes, we need 2 to the power of 33. Now, let's just make it such a way that all pointers are 33-bit wide, right? It's so easy, come on. Do you see a problem here? The problem is that you cannot increase a variable size by 1 bit. If you decide that all pointers will now be 33 bits, they will all actually be 64 bits, and your program just, all your variables and your random access memory usage just increased 2 times because all of your variables became 2 times bigger. This is why Windows still insists that the default size of integer is 32 bits, so that, even though it's a 64-bit processor, if you say that integer is 64 bits, all variables become 2 times bigger. And most programs, they just work in a very small fraction of random access memory, so they can still use a pointer which is 32-bit in size. The program still can be relatively small, and because each program doesn't really take more than 4 gigabytes of random access memory, rarely if any. So many programs still think that they're working on 4 gigabytes of RAM because Windows is doing some kind of emulation so that the program doesn't become like 2 times bigger, because all variables and all pointers become 2 times bigger and so on. So, that's maybe not so important for us, but generally this, like, wow, this is why 4 gigabytes is the limit of many computers. Well, the reason why the memory, the pointer size becomes from, instead of 33 bits to 64 bits, is that usually computers, especially, for example, 64-bit computers, they cannot address, for example, some weird odd sizes like 48-bit numbers. Well, they cannot address memory by 48 bits, for example, usually. They usually can read 1 byte, 2 bytes, 4 bytes, or 8 bytes at a time. So this is also some special thing that I can tell you for the first time. Maybe you already know this, maybe you don't. If you don't know this, you will have to learn it later in the next semester. If you study microcontroller programming, you will either learn or just revise what this attribute aligned for means in a C programming language. I think it's written something like that for C compiler and stuff like that. So when we study this, I'll tell you it again, but generally, let's say, for example, we have 32-bit processor. 32-bit processors work on 32 bits, and even though they use 8-bit memory inside, they should be able to somehow read all 32 bits at the same time. Otherwise, if you have 32-bit processor, but random access memory is just 8 bits, well, then you don't really gain any speed. Let's say you want to add two 32-bit numbers that are located in random access memory. You would have to read first number, 4 bytes, 4 times reading, and then the second bit number 4 times, because 4 bytes, and then you have to glue them together, and then you need to add them. So if we're talking about ARM processors, which are 32-bit processors, their memory is generally like this, but with some superpower in the following way. ARM processors actually have data out 32 wires, and they can select if they want to read just 1 byte, or if they want to read 2 bytes, This way they can read 16-bit numbers with just one read, or they can read 4 bytes at the same time. They give the bottom address, and they have this special select signal with which they select if they want to read just 1 byte, 2 bytes, or 4 bytes. It's a byte read, word read, or double word read. If it only reads 8 bits, then the top 24 wires are just not used. They're, for example, all zeros. But if you read, for example, one full 32-bit number, it will output all 4 numbers on these 32 wires, and the processor can this way read all 32 bits at the same time. So for example, you define 32-bit variable, the compiler automatically stores it over 4 bytes, for example, from memory 0 to memory number 3, and you can read it all with just one read. And for writing, the same. I'll write it in green because that is for 32-bit ARM Cortex processors. Instead of 8 wires, it actually has 32 wires. And the same way, it can also write 32-bit number with one write with one memory access time. And this way it really works much faster than 8-bit processors. It reads 32-bit number, does something, and then stores it back. But the problem is that the problem is that this method has one limitation that you might want to remember for your personal intelligence, and it is making it such way that these 32 wires are arbitrarily connected to all kinds of bits would make the memory very, very complicated and complex. And this is why the memory is made in such way that you select a byte, and these numbers, these, for example, 32-bit numbers, they need to start with an address that divides by 4. Okay, so you can store, for example, one 8-bit number in any address because you select with read select any address and it will output you the number. But 16-bit numbers can only be stored in addresses that follow one another, and the bottom address starts with a number that divides by 2. So for example, 16-bit number can be written in these 2 memory cells. It can be written in these 2 memory cells, but it cannot be written in the memory cells 1 and 2 because the processor cannot read them in such way. So 16-bit number stored in memory addresses that start with an odd number, impossible, because memory is just wired in this way. And for 32-bit numbers, they must start at addresses that divide by 4. So for example, a 32-bit number can be stored in all these 4 memory addresses. So I'll write it here, 32. And the next 32-bit number can be stored in next 4 addresses, 32-bit number. But you cannot store the 32-bit number in such addresses that start with some odd number, 1, 2, or 3, or 5, 6, and 7. So you cannot, for example, store it like this, because this address will be 4, this will be 5, this will be 6, 7, 8, 9, and so on. So this way it would be stored in addresses 6, 7, 8, 9. 6 does not divide by 4, so it's impossible. So either you personally, if you write it in assembly language, or compiler is smart, it knows it, and it automatically does this process, but it stores 32-bit variables only in such addresses in which first location, the bottom part of this 32-bit number, is stored in an address that divides by 4. Why is it important to know? If you make structures in your C programming language, struct, and then you have variable, for example, int 16t, int 32t, and int 8t, for example, then actually, for example, if you make this structure, in reality, this number will be stored in an address that divides by 2, but sometimes it can happen that it's stored in a memory location that divides by 4. In that case, this thing takes 2 bytes, this thing takes 4 bytes, this thing takes 1 byte, but if this 16-bit number is stored in a memory location that divides by 4, then the compiler secretly puts 2 bytes empty, this is called padding, between the 16-bit number and 32-bit number. Because if this is located in a location which divides by 4, which is actually what the compilers do by default, they usually store variables and structures with a at address that divides by 4. Well, 2 bytes are taken by first variable. The next is 32-bit. It cannot be stored in this 6 and 7 address, so it skips 2 bytes and it actually takes the next 4 bytes. And the 8-bit number will just take the 9th byte. So when you run size of this structure, it will return you 2 plus 4 is 6 plus 1 is 7, but because 16-bit number is, well, usually structures always start at address that divides by 4 for faster read and write operations, the size will actually return 9 instead of 7, because 32-bit number must be stored in a location that divides by 4. Structure beginning will always be stored at a location that divides by 4 for faster pointer access. And so you get 16 bits here, then 2 bits empty, and only then the next variable, and then the final variable. Okay? And if you make an array of such structures, then after this 8-bit number, to store the 16-bit number of the next structure element in array, it will put either 1 or 3 byte padding, depending on implementation. So this is why you kind of have to know this. This is why if you want to avoid it, you will need to use either attribute packed or just order these variables starting with the biggest. So for example, first 32-bit numbers, then 16-bit numbers, and then 8-bit numbers if you want to. Then you will not have any padding, for example, in this case. This starts at address that divides by 4. This will start at the address that divides by 2. And this can be put in any address, so it will just be added to the end. So there will be no padding. And the size of the structure will be 7. Okay. Yes, padding wastes memory, but padding makes the program access data faster. Okay, so padding wastes memory, but it makes a program run faster because it uses this memory acceleration where it can read 32 bits or 4 bytes at the same time if they start with an address that divides by 4, and 16-bit numbers 2 bytes at a time if the first byte is located in an address that divides by 2. So why the size of structure would be 9, not 8? This is 4 bytes, this is 2 bytes, it is 6 plus 1 is 7. But when we swap this and first wrote this 16-bit number, it added 2 bytes in between. So 2 plus 2 is 4, 4 plus 4 is 8, plus 1 is 9. So in this case, it will be 9. Okay, this is, if you ever come across the situation where your compiler uses padding, well, now you know why it uses the padding, because memory is built in such way that it accesses faster, just as I said, blah, blah, blah. Okay, now let's continue analyzing this whole situation. So if we wanted, well, for now, I'll just not talk about this 32-wire acceleration, which is for 32-bit processors. Now just let's look at a very primitive, simple, basic 8-bit microcontroller, which has 8-bit data wires in and 8-bit data wires out. The question is, what is the total number of cables necessary to connect this memory to the processor? Well, I will just add that there's also a power supply, so VCC and GND. This is how they're usually called. So supply and ground is 2 pins. And so let's just count together how many cables do we have. So we have 8 data cables plus 2 signals clock and write enable plus power supply and ground plus 15 cables is for address selection, for writing, 15 cables for reading, and 8 cables for data. The total is 50 cables, okay? 50 cables. How do you think? Is it good? Is it bad? Is it a big number or small number? Well, actually, I can just tell you that it is a lot of cables for relatively small memory. And if we're talking about simple, stupid microcontrollers that should cost a few cents a piece, or maybe €2 a piece, 50 wires would be, a forest of wires, lots and lots and lots of wires coming into this memory cell and from the memory cell to the processor and back. So, and let's say we want a bigger memory, you would need to have 2 times more cables. For example, you want to add, you want to double the memory, you need to add 2 wires, one for wire select and one for read select. This is why, because, first microcontrollers were built maybe 40 years ago, where people didn't have super duper computers and really cool 3D animation um, device design applications. They did a lot of this work on paper, with a pencil and the paper, so they wouldn't be able to connect 50 wires just like that. And it would also cost a lot of money to have so many wires not crossing somewhere, going from the processor to memory and back. So for the economical reasons, and also for reasons to designers not to go crazy because of the overload of their brain, write select and read select are actually connected together. Okay, and the name will just be address. This way you can use the same data bus to select for reading and for writing. And if you want to, for example, read, you just set write enable to 0, put the address of the byte that you want to read, and it will appear on the output. So I don't know, you set address equal to 3, and this 120 will be put on the output, and at the same time you keep write enable 0 so that nothing is overwritten accidentally. And if you need to write, well, you don't care that there will be some data output on the output. You just select the byte that you want to write. For example, I don't know, byte number 2, you set address equal to 2, you set write enable high, you input the data, and it will be just written to the address number 1. The only limitation is that you cannot read from one data location and immediately store this value to another data location. So you cannot read and write to the memory at the same time, because the address will be selected in both ways, and you'll just copy the value of a memory location to itself, because write select and read select addresses are the same. This is why all processors, all microcontrollers have this thing that if you want to copy memory from one location to another, one number or 500 numbers, doesn't matter. You first read the number into the processor, into this general purpose register block. For example, I don't know, register R5. And then you store the value of register R5 in another location that you select with the next address. So you want to read, for example, from address number 0 and copy it to address number 3. So you first set address equal to from 1 to 3, so equal to 1. Data at the output will be 77, and you read it to register R5 equals 77, right? You read it into this register. Next step is you set address, I don't know, with different color, for example. You set address equal to 3. You connect register R5 output to data equal to R5 equals 77. And you set write enable high, and you this clock from 0 to 1. And during that time, this address number 3 will be overwritten by 77. Okay, so it takes like 2 actions to copy memory from one location to another. So this is all about microcontrollers. Desktop processors, well, they are high-end machines, and you know, they can afford to have more cables for more speed. And this is why desktop computers cost several hundred euros, and the processors, for example, Intel processor costs 300 euros. Well, because it has a lot more cables and a lot more transistors inside. But microcontrollers, which are really basic devices, and ARM architecture in general, uses this method so that the chip costs 5 euros instead of 500 euros. Okay, so we had a question in the chat. Oh, no, it just says 50 wires. Okay, maybe it's an old message, sorry. Okay, so this is about the cables. And the next thing is, so right now, instead of 50 cables, we have 35 cables, 35 wires. And the next thing is, well, if you think about it, if we can only read or write at the same time, well, then if we read, this data in is unused. And when we write, then this data out is unused, because we're not using it for writing and we're not using data in for reading. And this is why actually in the processors, in the memory, data in is actually connected to data out. Now I will need to erase something a little bit to have the space to show you this. but actually data in is connected to data out, and we will have a two-way data line, which can output the data if you're reading in the read mode, or it can read in data that is output on this bus when we are writing it into the memory. However, let's say data in a certain location is 0, and microcontroller wants to write 1 into that location. If this cable is set high to 1, but this data output sets the same cable to 0, you will have short circuit, and either the memory will burn or the microcontroller will burn, because this Q output is active output. It either connects the line to ground or to power, and if the microcontroller puts active 1 and this thing shows active 0, it's a short circuit and it will burn. This is why, instead of connecting them together directly, we will introduce a new element, which is called three-state buffer. So I'll just write its name. Three-state output, or let's say three-state buffer. And it works in the following way. Quite simple. So data connects here. So we can read whatever we output, we don't care. Data in is high impedance reading signal, so it doesn't output anything. So it reads whatever is on the data line. And we will actually call this line simply data. But output line is connected to this thing, and it is controlled by write enable signal. So, except we will also need an inverter here. But generally, it works like this. As you know, the output of this thing is these two MOSFETs, which if input is so the output is push-pull MOSFETs. So either they connect the output to power supply, or they connect it to ground. But if we disconnect their gates, they don't output anything. They're neither connected to ground nor to power supply. As a result, this output doesn't output anything. So it doesn't bother with microcontrollers information. And this gate signal is just basically disconnected by this write enable signal. So, and it works in the following way. If we set write enable to 0, write enable is 0 means we want to read data. Then this control signal is 1, and data Q is connected to data and basically outputs the data. And microcontroller, on the other end, has the same three-state buffer in reading mode. So microcontroller controls its own input and also the input of memory with this write enable signal. So that's for reading. Microcontroller is in listening mode, and this thing is in output mode. However, if we set write enable to 1, then this output enable is 0. This thing is switched off, doesn't output anything, and then data comes from microcontroller into these data lines into the memory and is written into the memory. And this is called three-state buffer. And actually, all microcontroller pins are three-state, because if you take, for example, Arduino microcontroller or any other microcontroller, you can tell its pins to either be input or output. And if it's output, either output low or high. It is done exactly with this 3-state buffer. If it's output, then either it will be high or low. And if it's input, then at the same time, high and low are disconnected, and it's input. It's not giving anything out and it cannot burn anything. So this is how memory is organized. And as a result, if we connect data in and data out together with this safety 3-state buffer to avoid short circuiting it with the microcontroller, then from 35 wires, we are down by 8. It's 27, I think. It's only 27 wires. And it's still a lot of wires, but it's manageable, and it's the smallest number of wires that we can have. It's mathematically impossible to have even less wires at this particular configuration. So if you don't believe me that it's the case, you can go in Farnell, you can find some kind of parallel memory. So serial memory is totally different thing. We need parallel memory. Parallel NOR, for example, show me the results. And as you can see, these processors, well, they have lots of pins, lots of cables here. Microcontroller memory is just on chip directly connected, but also has these cables. Now let's see its datasheet. What inputs and outputs does it have? So there it is. You can buy this chip if you want to. And so what do we have here? We have address pins, as you can see, address 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So since, oh, and also A17. 17, does anybody see 19 or 18? No. So if the largest data signal is A17, counting from 0, it has 18 address signals. So it means that the largest number of memory entries is 2 to the power of 18. So 2 to the power of 18 is 262 divided by 1024. So this memory is 256 kilobyte memory, and I just read it from the number of address lines that it has. Next, as you can see here, it also has data, and its name is DQ because D as input and Q as output. So it reads new values or outputs its old values through these data lines, data from 0 to 7. So it's just 8-bit memory. It's a regular 8-bit memory. And the control signals, oh, also here's the supply and ground. And control signals are a little bit different, but basically almost the same as what I described. So this chip has chip enable signal. Basically, if chip enable is high, this chip is totally switched off, so that you cannot accidentally overwrite some data. So if you want to write, you need to set it low. Also, it has write enable. It's the second level of security. So chip enable switches the chip on and off for writing or reading, and write enable switches the chip for writing. So if you this hashtag means that it's active low. So if it's high, it's not writing, but if you set it to 0, it will write the value set on these D pins into the address selected by A pins. And output enable signal switches the data lines between reading or writing. So output enable means output the number. So when it is, and it's hashtag, so it's inverted. So if it's low, then data lines output the number, and microcontroller should be in read mode and read that number. And when output enable is high, then data lines are in read mode, and microcontroller can send the number to this memory and write it to the selected address selected by A lines. And so this chip enable signal, what it allows you to do is it allows you to use multiple such chips in the same system. You just put, for example, two of them. If you want to write into the first chip, you set its chip enable active and write to it, and the other chip enable you switch off. And if you want to write to the second chip, you set first chip's chip enable off and the second chip's chip enable active. In this case, they're inverted, but whatever. And so also you would ask me, where's the clock signal? Well, this thing writes data in a little bit special way. Also, you can buy them in different packages. And here it is. So read operation. The read operation is controlled by chip enable and output enable. You select address that you want to read with address. Then you select chip low to switch on the chip. And then you set output enable low, and it will output the value of selected address on the data lines. Programming is a little bit more complicated. So after you have read the data, you just set chip enable off, so the chip is off. Programming is a little bit different. Well, first of all, you need to erase the whole memory before you can start writing to it because it's a flash memory. But then if you want to write a byte, so first you select address in which you want to write, and then you set the data lines to the number that you want to write into the selected address. And then you need to set chip enable and write enable low, and write address is selected or latched. In this case, it's called latched because it is like photographed on the falling edge of either chip enable or write enable, whichever occurs last. So you set chip enable low, write enable low, and as you set write enable low, it photographs the address. After that, you can change the address or some noise can, damage the address, but it won't be ignored because it photographed the address when these signals went low. And then data is latched on the rising edge of either of these signals. So on falling signals, it uh, read the address, and on rising edge of, for example, write enable, it reads the data. And then the third step is the internal programming operation, which is initiated after the rising edge of the fourth write enable or chip enable signal. So you need to set write enable high, low, and high and low, and only then it will write the data to the actual memory cell. And as you can see, it takes around 20 microseconds to write. So this flash memory is kind of, special and a little bit sophisticated. There are also memories. Well, flash memory is just slower to write. This is why it needs 4 clock cycles to write. For example, random access memory writes and reads instantly. It doesn't need these 4 clock cycles, but flash memory is slower, but it stores the memory between power outages. So this is why it's that way. And this is for writing. So in this case, it's like write enable is like a clock signal. Chip enable you would want to keep low all the time because otherwise the chip will be deselected. But this write enable works the same time as write enable and also as write clock. Okay, and also the last thing that I can mention is we have a clock. We have also memory in Logisim, and I'll just quickly show you. So under memory tab, we have RAM and we have ROM. ROM is really simple. Since it's read-only memory, you just give it an address and it will output a data, whatever is written in the selected address. And there's this select signal, which is basically enable this chip signal, but we will not just use it. It will be always one. For random access memory, you see there is address, there is data, which is data in and out. Select signal selects between data active and inactive. This load is output enable signal basically, and this clock signal, its description says memory value updates on rise from 0 to 1. So select address, select data, and when you have clock going from low to high, the data on data line will be stored in address selected by address line. So you need to end this with a write enable signal, and only then it will be safe to use. But generally it works like this. Theoretically, this memory cell also has other options, like one asynchronous load and store port, which basically doesn't have a clock, and separate load and store ports where it has two data lines, data in and data out. But as I mentioned you, most memories, basically almost no memory has it, so it's just like this. You will have to use them later in the labs. Okay, so it's 6 and 6 minutes, so I guess we have to finish this lesson. If you have some questions, you can ask. Otherwise, we will do the labs. By the way, because of this COVID thing, as far as I know, we cannot have even the labs at school. So you have to do them at home. Okay. On Friday, they made extra these rules for this COVID thing. So tomorrow, just if you want to do it tomorrow or you want to do it on weekend, switch on the computer, go to Artus, there you find the lab description and video, and you do the lab, upload your progress, and then you're free to do other stuff, whatever you want. Okay, so don't come to school, it's dangerous. Yeah, do it at home, do the lab at home.